Hello, welcome back. We're going to be moving on with our hypothesis testing to look at one and two-tailed tests. A good example of a two-tailed test will be what we're going to talk about today, which is testing the claim of M&Ms. So Mars and Mars, the company that makes M&Ms, they claim that 20% of all their M&Ms are orange, and we're going to open up a bag of M&Ms and test that claim. We'll actually be doing an M&M lab in 2 weeks. It's going to be a ton of fun. So we're also going to be inputting our data into a Google Sheet, which is a live document. So you guys can actually input the data at home as well. So if you guys have access to M&Ms, that's awesome. You can actually do our lab with us from home, which will be great. It'll be a good way to have you guys be more interactive with what's going on in class with some of our labs and activities. So I think you guys will enjoy that. So the claim from Mars and Mars is that 20% of all of their M&Ms are orange. So our null hypothesis will be assuming innocent to proven guilty. So it's going to assume that it's actually still 20%. So the null hypothesis is that the true proportion is actually 20%. Now the alternative hypothesis is going to be two-sided, because we're not only interested in if it's more than 20% or if it's less than 20%. Either one would be alarming to us, and so we're going to just simply say that the proportion is not equal to 20%. So that would be a two-sided test, because we're actually interested in being higher or lower than 20%. So next step in our process for hypothesis testing is to select an alpha level. So we always select an alpha level before we find the p-value. That way we can't be accused of kind of like cherry picking, but basically picking an alpha level that kind of goes along with the conclusion we were looking for in the first place. So we always default to a 5% alpha level. Sometimes we'll do a 1% alpha level if it's really important that we don't make a type 1 error, which is that we have a false positive, or that we sound the alarm and say that there's an issue when there really isn't. So in this case, we're trying to call BS on Mars and Mars. So is it really important? I mean, we're talking about candy. It's not super duper important. If I called up Mars and Mars and told them that we thought that they were lying, is it okay if I'm wrong 1% of the time, or that I'm wrong 5% of the time, or 10% of the time? Because that's how much the random sampling variation would occur, and we would get samples that were like that even though we had the true population proportion of 20%. All right, so the standard deviation for our sample proportions is going to be based on our hypothesized proportion. So the whole p-value is calculated based on the assumption that the hypothesized proportion is true. So if that hypothesized proportion is true, like it's actually 20%, then the probability of getting a sample proportion like we saw would be a certain p-value. So p naught times q naught is going to be a hypothesized value of 20%, which is what they thought. So 20% times 80% divided by our n. So we're actually on the assignment. If you want to go along with us in the assignment, this is all example 1. So suppose there's supposed to be 20% orange M&Ms. A bag of 114 M&Ms has only 28 orange ones. Does this contradict the company's claim? Or is that enough evidence to contradict the claim? So 28 out of 114. So our n is going to be 114. And if we put this in the calculator, we get a standard deviation of about 3.7%. So if the true proportion was 20%, then with a standard deviation of 3.7%, you can actually fill in the numbers that we have here. So what was our sample proportion? And then with a sample proportion, what was the alpha level going to be? So if we were having a one-tailed test, then we would go to a standard deviation of 2.3 in order to have 1%. So that would be the top 1%. So our observation would have to be more than 2.3 standard deviations above the mean, or below, depending on which tail we were doing, left or right tail. If we were doing 5% alpha level, then we would have to go to a z-score of 1.65, or be in the top 1.65 standard deviations above the mean or below, in order to be in the top 5%. And to be in the top 10%, we would have to go to 2.28. Now, if we're doing a two-tailed test, whatever we have on one side, that probability actually gets doubled. So it's actually going to adjust the values here. You can see it better on this side. So to be in the top 1%, now you will have half a percentage on this side and a 0.5% on this side. So basically, instead of having to be at 2.3, now we actually have to be at 2.58. So it's even harder because your p-values get doubled. So if you have a two-sided test, it's actually even more difficult to show, to be able to reject a null in that case. And then instead of going to have 5%, you go to 1.65. Now we have to back it off to 1.96 because we have 2.5% on both sides. Same thing with, instead of having 10% at 1.28, we get 10% by going on both sides to 1.65. So again, it's harder to prove to be able to reject the null hypothesis, or to have a powerful test and be able to reject the null hypothesis when we're doing a two-sided test. All right, so our assumptions and conditions, the first one is it a random sample? In other words, do we expect it to be a representative? So if we have just a random bag of M&Ms that we grab, it should be a random sample. It should be independent, in other words. So the population, which is with the Greek letters, the hypothesized proportion was 20%. So of all the M&Ms that exist, 20% supposedly are orange. And then from our sample, which was a bag of 114, of that we found 28 out of 114, which is 24.6 roughly. You can do the exact fraction if you prefer. So our sample proportion was higher than the hypothesized proportion, or P naught. But is it high enough that it would be considered unusual? Well, it's going to be a little bit over one standard deviation, so then we just have to find the p-value at that point. Okay, but it should be representative because it is random. All right, independence, we're sampling without replacement, so it's not actually truly independent. The probabilities are changing, but because we're sampling less than 10% of the population, less than 10% of all M&Ms, the probabilities are going to change so small, like sampling without replacement, like marbles, that, I mean, every time we open one, there's fewer M&Ms out there. But as long as we're sampling less than 10%, it won't change our probabilities enough to change the overall conclusions. Then is it appropriate, the success failure condition, is a normal model appropriate? So all of these calculations are based on z-scores and normal models, and so we have to make sure that we have at least 10 successes and 10 failures, meaning we have at least 10 orange M&Ms and at least 10 that are not orange M&Ms. That'll guarantee that we have 3 standard deviations unobstructed by a hard left bound of 0 or hard right bound of n, whatever that value is. So the question is a sample proportion, it's actually 0.246, I believe. Okay, so is a sample proportion of 0.246 a statistically significant observation, or could it have just occurred by chance? So it is higher than what we would expect, but we also expect samples of that size of 114 to have a certain amount of variation, and so the question is, how far is it from what we would expect? So our standard deviation was 3.7%. So if we go over to where our value is here, on one side it has a basically a p-value of 10.9%, and it's two-sided, so we actually end up doubling that. So we have another 10.9% over here. So the overall p-value for our observation that we saw, because it's just slightly over one standard deviation, would be about 22%, or 21.8%, which is a higher p-value than any alpha level that we would use. We only use alpha levels of 1, 5, or 10. And also remember, we selected an alpha level of 5%. So we can't change our alpha level now that we know the p-value. That would be dishonest. Let's put it that way. So remember, we always presume innocence, which is the null hypothesis, until we have enough evidence to statistically significant evidence to be able to prove guilt, which would be rejecting the null hypothesis in favor of the alternative. So our burden of proof is different. Like if we remember how O.J. Simpson lost the civil court, but he won, or he was found not guilty in the criminal case, the criminal court. The reason for that is the burden of proof is higher in the criminal because the punishments are also more severe as well. We're not just talking about money, we're talking about time and life, right? So if we had an alpha level of 50%, that would be like a preponderance of evidence. It's just more likely that it happened than it didn't. Beyond a reasonable doubt would be like an alpha level of 1%, meaning 1% of the time we would be wrong by normal sampling variation, but it would have to be the top 1% of samples in order for that to occur. So what did we do with the high p-value? We had a p-value about 21.8%. If our p-value is greater than our alpha, then we fail to reject the null hypothesis. If the p-value is less than the alpha value, the level burden of proof or the level of significance, then we would have enough evidence to reject the null hypothesis in favor of the alternative. So in this case, because our p-value was greater than our alpha of 5%, because 21.8% was greater than 5%, we failed to reject the we fail to reject the null hypothesis. Now, there actually could be, it could be more. We'll get into this a little bit later. It's the power of the test, but maybe we just didn't have a large enough sample in order to reduce the standard deviation. Maybe the true proportion actually is like 24%. But because we had such a small sample, it was just one small bag of M&Ms that we opened up, we weren't able, our test wasn't sensitive enough to be able to detect that, at least with a small enough standard deviation to be able to have, to detect it any other way. So we will actually be putting all of ours together and opening a bunch of small fun-sized bags of M&Ms together. So let me actually open that up and show you. So this is my Google sheet that I made today. Pretty awesome. So I have all of the students' names. These are, if you recognize these names, they're from Guess Who. Yeah. So just for FERP, I wasn't sure if I could put your names on there, but your names will be on there for the other document. All right, so on this one, basically, we have 3 trials, so I'm going to give you guys 3 bags of M&Ms. For the first trial, you just put the number of orange ones that you have. So let's say Bill had 3 orange ones out of 17. So just put that in there, and then it should update as we go. And over here, it's going to be graphing out the cumulative total, the cumulative relative frequency, which is going to be the percent of M&Ms. So this relative frequency will actually approach the true empirical probability as our sample size increases because of the law of large numbers. And so we'll actually see how as each person puts in more and more, opens more and more bags of M&Ms, and after we get it all together with all 25 of my stats students, it's going to be really cool to see where this goes. Then let's say Bill opens another one and he has 4 out of let's say 17. Let's do 18. You'll see it'll just keep adding on there, and these don't have to be in order. So it's not like you have to wait for everyone else to fill it in. You can just do yours and it'll keep updating it as the data comes in, which is really, really cool. All right, cool. So wanted to show you that. This is basically, and it's a live document, so each person can edit it as we go. So even if you do it at home or in class or during 4th hour or whatever, it doesn't matter. We'll still have the data, and everyone can see what's happening in real time, which is cool. All right, so what do we do with the high p-value? We fail to reject the null hypothesis. So the p-value is a conditional probability. It's based on the condition that if the null hypothesis is true, meaning the hypothesized proportion is the actual true proportion, then the probability of observing a sample statistic at or worse what we observed would be that specific probability, the p-value. So if our p-value is 0, that's incredibly rare, meaning that it's not possible that the true proportion could exist. The true proportion was the null from the hypothesized proportion. If it's 1%, that would be considered highly significant or overwhelming evidence. 5% is strong evidence or significant, which is like 2 standard deviations away. Weak evidence or not significant is anything less than or greater than a p-value of 10%, and then anything more than that wouldn't be no evidence. So a 2-sided alternative test is whenever we have, we're just interested in not being equal to. So if we're just saying, okay, it's not 20%, it could be greater than or less than 20%, both of those we'd be interested in. Oftentimes we were actually going to have a one-tailed test, which is when we're only interested in one side. We want to know, has the defect rate decreased strictly, or has the amount of sales increased? We don't want to know if it decreased. We want to know if our number of sales increased this year or something like that. So oftentimes it's only one-tailed, but sometimes it is two-tailed like we did today. Number 6, so we're on the assignment, moving right along. Cars. Survey investigating whether a proportion of today's high school seniors own their own cars is higher than it was a decade ago, finds a p-value of 1.7%. Write the null and alternative. So the null is that the proportion of high school seniors today that own their own vehicle is the same as what it was a decade ago. So there's that the true proportion is they didn't tell us what that proportion was, but that it's equal to that proportion will be the null hypothesis, which is another way of saying the percent of high school seniors who own their own cars is the same as it was a decade ago. And then the alternative, we want to know if it's higher. So it's a one-sided test. We do want to know if the proportion is greater than whatever the null was from 10 years ago, a decade ago. So, which is another way of saying, has the percentage risen? Is it reasonable to conclude that more high schoolers own their own cars? So with the p-value of 1.7%, it depends on what we set the alpha level to. More than likely our alpha level would have been 5%, and because this p-value is less than 5%, that would be enough evidence. But if we were being really cautious, we wanted to have a burden of proof of an alpha level of 1% because we were really afraid of type 1 errors for some reason, then this might not be statistically significant. So we might actually have to increase our sample size in order to be have enough sensitivity to be able to detect the difference between the two. So is it reasonable? Yes. Assuming the rate was the same, only 1.7% of samples would be this high. That's statistically significant. We have enough evidence to reject the null hypothesis. In other words, because the p-value is less than an alpha level of 5%, then we can reject their null. Number 14, abnormalities. In the 1980s, it was generally believed that congenital abnormalities affected about 5% of the nation's children. Some people believe that the increase in the number of chemicals in the environment has led to an increase in the incidence of abnormalities. A recent study examined 384 children and found that 46 of them showed signs of an abnormality. This is strong evidence that the risk has increased. So we're going to assume our null hypothesis is that it's still 5%, and then our alternative, we want to know if it's increased. So we want to know is the proportion now higher than 5%. So our null is that the true proportion is 5%, which is that the percent of congenital abnormalities is the same. And then the alternative is going to be a one-sided, which is going to say that the proportion has increased. We're not interested if it's gone down. We want to specifically know if it's increased. Check our necessary assumptions. Was it a random sample? They didn't tell us it was a random sample, so we got to be careful. Where did they find these children? Did they go to a hospital, like the children's hospital, and then they examined 384? Well, if you were born with congenital abnormalities, you're more likely to be in a hospital, so that would not be a random sample, right? That would be a convenient sample. So we need to make sure that these children are randomly sampled. That way we can make sure that they are a representative sample. So we do need to mention that might be an issue. 10% condition, there's certainly more than 3,840 children, so that we're sampling less than 10%, not a big deal, even though we're sampling without replacement. Success failure, we found 46 that had signs of an abnormality, which is more than 10, and we obviously had more than 10 that didn't have congenital abnormalities as well, so those are fine. Perform the mechanics of tests, find the z-score and the p-value. So I'm going to show you how to do this on the calculator because it's a whole lot easier. I need to go back so that I can see the things here. All right, so we're going to go to stat and then arrow over to test. We're going to do a one proportion z-test. It's a z-test because it's based on z-scores because it's from a normal model. Now our hypothesized proportion is going to be 0.05. The number that we found was 46 out of 384. And then the proportion we want to know, is it equal to the null proportion or P naught? Is it less than P naught or is it greater than P naught? We want to know specifically is the true proportion greater? So has it increased? So it's a one-sided test. Then we hit calculate and it will find the p-value for you. Also the z-score is calculated for you as 6.27. The proportion, the p-value, the probability of that occurring is basically 1.75 with 9 zeros in front of it. So it's like 0.000900175, which is, if I do the p-value and the reciprocal of the p-value, it's basically 1 in 6 billion. So there's a 1 in 6 billion chance. If it's still 5%, there's only a 1 in 6 billion chance that we would find 46 out of 384 children, because it's way above 5%. In fact, the sample proportion we had was about 12%. And with the large enough sample that we had, that would be 6 standard deviations and incredibly rare, like we said. 1 out of 6 billion samples would be that high or higher. So that would be overwhelming evidence. Now the big issue I would have is was this a random sample? Okay, so if they went to a hospital, then you can't do that because those are not independent and that's not a representative sample because healthy kids don't go to the hospital. All right. All right, perform the mechanics of the test, find the z-score and p-value. So our sample proportion that was given to us, the z-score was given to us from that putting in the calculator. The standard deviation, we can calculate that. I'll go ahead and show you how to do that real quick. So that's going to be the square root. All right, so 0.05 times 0.95, there we go, divided by 438, I think. 384. I said 438. 384. Okay, I had the right numbers, just all dyslexia up. Okay, so that's our standard deviation, all the good stuff. And then the probability of that occurring, we said, was incredibly low. So carefully explain the p-value. So if the proportion of congenital disorders or whatever is still 5%, and the probability of observing a sample proportion with that is 6.3 standard deviations above the mean is that probability, or 1 in 6 billion. All right, what's your conclusion? Well, with the p-value that's essentially 0, we would have enough evidence to reject the null regardless of what alpha level we selected. We do need to select an alpha level before we find the p-value. That way we can't, go back and change our results. So yeah, we didn't select an alpha level, but it wouldn't matter because regardless of the alpha level, it's not going to happen. We have enough evidence for any reasonable alpha level to reject the null hypothesis. Do environmental chemicals cause congenital abnormalities? Okay, so we have evidence that we believe that the proportion of congenital abnormalities has increased, but as long as it's random sample, of course, that's a big question mark there. But we cannot prove a causal relationship without a carefully designed experiment. So correlation is not equal causation. That still applies here. So without a carefully designed experiment, we can't do that. In case you're wondering, there was a guy on Reddit who ate a bag of M&Ms. You can see all the dates that he ate bags of M&Ms, and he actually graphed out the distribution of the colors. So you can actually kind of see it here. It's kind of cool. We're going to be doing far greater sample size for our simulation with just having you guys collect all the data. So we're only going to be focusing on the orange M&Ms as well, make it a little bit easier. So looking forward to that. Please let me know if you have any questions. I've decided we're not going to do the quiz for the confidence intervals. We did the practice test or the practice quiz, so you kind of already got your practice there. We will do a practice test, and we'll take the test before spring break. So it won't end up being that big of a deal. So I want to make sure we had enough time to do the lab and class and stuff like that. So I'll see you guys later. Let me know if you have any questions.